All right, we're going to talk about optimization, and this is a type of problem in calculus where we are trying to find maximums in given situations and minimums in a certain given situation, and it's really a section of word problems, different types of word problems that all involve this finding the maximum or minimum given certain constraints and real world problems. We're going to start off with problems that we're not going to do the whole thing. I'm going to give you pieces and show you where we would go from the pieces that I've given you. And then in the second part, we're going to do problems in their entirety. Okay, so in these ones, we just want to solve the problems, but I've given you the constraints, we call them, and the equations as well that we're trying to minimize or maximize. So in this first one, it's an example of production cost minimization. So we have a function for the cost in a for a business or whatever, cost of production of some item. Okay, X represents the production quantity, so how many things you're producing, right? And we want to figure out what is going to minimize the production cost. All right, and we're going to use calculus to do this. Now this one, we have just one variable, we have the function, we want to minimize it. And so really what all we're doing is applying what we learned in the last section about finding derivatives, finding critical points, and then evaluating, is a minimum or a maximum based on the critical points that we have. So let's start off just by finding the derivative. C prime of x is going to be equal to x squared minus 6x minus 16. And then we want to find critical points. That's where the derivative is 0 or does not exist. There's no place where this doesn't exist, so we just want to figure out when is this 0. We're going to do that by factoring. So this is going to be x minus 8 and x plus 2. All right. Now we would set each one of these equal to 0, so we'll get x equals 8 and x equals negative 2 for the critical points. But in the context of this problem, we can't have a negative production quantity, right? So we can disregard x equals negative 2. We don't need to worry about that. So we'll make a little sign chart here. We'll put 8 on it. Okay. We'll test the point to the left of 8 in the derivative. So c prime of 0 would be 0 minus 16, so that'd be negative. Pick a number like 10. If you plug in 10 here, you get positive times a positive. It's positive, indicating that at 8 we have a minimum. Okay, so 8 units is going to minimize the production cost in this situation. All right. So in an actual problem, you would probably have to set that up. But again, we're just trying to kind of baby step into these problems here. All right, let's look at this next one. Fence area maximization. So here's what we have. We want to maximize the area of a rectangular field. All right. And by the way, I should have said this before. We're going to talk a lot about the objective function. That is the function that we are trying to minimize or maximize. So in this example here, the objective function was the cost function. We are trying to minimize cost. So this was the objective function. Okay. Over here, when we're trying to maximize area, the area function is going to be our objective function. Okay. So our objective function is right here. Okay. Objective function is for area. All right. W is the width of the field, so we can label that. This is W. All right. And we have a constraint. We have only 200 feet of fencing. So we want to know what is the width and length that are going to provide the maximum area here. And you can see from our area function that if our width is W, then that must be our length of the field is going to be 100 minus W. So this is 100 minus W. All right. That means that this is also W here and that this is 100 minus W here. So this one, again, we're given the function for area, and we want to maximize this or figure out what the maximum is. So A of W is equal to, this is 100, or if we distribute the W here, we get 100W minus W squared. When I take the derivative of that, I get 100 minus 2W. And again, we're looking for critical points here, so when this is equal to 0 or doesn't exist, we're only worried about when it equals 0. So we set this equal to 0. I'm going to run out of space here. When you solve this, you get W is equal to 50 feet. Okay, so if we want the dimensions, then the dimensions of this would be 50 feet by 50 feet. 50 feet by 50 feet. Okay. All right, so that is how we would approach that one. This one happens to be a square, maximizes the area there. All right, let's turn up the difficulty a little bit here and add a little bit more complexity to the problem. So let's look at the cylindrical can problem here. All right, we have, again, so we're going to maximize the volume of a cylindrical can. All right, so what's our objective function? Well, our objective is to maximize volume, so our volume function is our objective function. Okay, that's the thing we're trying to maximize or minimize. So here's our volume formula here. You can see this one has two variables. Okay, so I can't just jump right into deriving it. Well, I could, but we're not going to have enough information to deal with the result there if we do implicit differentiation. It's not going to be helpful. So I also have a constraint on this. All right, so if we want to maximize volume without a constraint, the volume could be anything, right? And so we have a constraint. We want the total surface area is going to be fixed at 100 square inches. Okay, so we can't have it any bigger than 100 square inches. Here is the equation for surface area in this situation. Now, if we give a rough sketch here, so here's our cylinder. If I sketch in R here, and this would be my height here, that's all the information we need to find the volume of this thing. Okay, and then the surface area would be the top of the can, the bottom of the can. That's that 2 pi r squared that's given there. Okay, and then this piece around is 2 pi rh. And we're not going to get into why that is, but we could deduce that. Okay? That has to be equal to 100. So the volume function is what we're trying to optimize. That is the objective function. Too many variables, though, r and h. So we needed this other function, this constraint function. And you don't always have to call it a constraint function. It's just another function that we can use to help us. If we have two variables or two unknowns, then we need a second equation to help us out here. All right, I called this a function. I'm sorry, this is just an equation. All right, so what I'm going to do to help myself here, if I'm trying to optimize pi r squared h, then what I'm going to do is take over here on the right, let's go a different color here, I'm going to take that 2 pi r squared plus 2 pi rh equals 100, and I'm going to solve this for h so that I can eliminate the variable h over here on the left. Okay, so I'm going to minus 2 pi r squared. I'll get 2 pi r h equals 100 minus 2 pi r squared. Then I'm going to divide by 2 pi r, so I get h is equal to 100 minus 2 pi r squared divided by 2 pi r. Okay. All right, and you could simplify this if you want to, but you don't have to yet. All right, so now we're going to take and plug that in over here to our volume function. So we have v is equal to pi r squared, and this is going in place of h. So in place of h here, this pen is skipping on me here. So in place of h, we're going to put 100 minus 2 pi r squared, okay, divided by 2 pi r. And then we're going to clean that up a little bit. So these pi's drop out here. One of the r's is going to drop out. So I get v is equal to, this is going to be r times 100 minus 2 pi r squared divided by 2. I could have put that all in the numerator. It would have been fine. All right, these 2's are going to drop out. This is going to become 50. And so I'll end up with v equals 50r minus pi r squared. Oh, sorry, pi r cubed. Okay, and then from there, we would take the derivative, find the critical point just like we've been doing. Okay, but I don't want to finish that out. I just want to show you that sometimes we'll need to have two equations and two unknowns. All right. Let's go on to package design here. So in this one, we're trying to design a package that minimizes the surface area of a rectangular package in which the base is a square. Okay, so what's our objective function? Our objective is to minimize the surface area. The function is going to be the surface area function then. So this is my objective function right here, surface area. Okay, you can see surface area of in this situation. So let's just sketch it out on the diagram here. This would be x, this would be x, and then this would be y. So the volume of that would be x squared times y. Okay. And you can see that function there, but we're not trying to minimize volume, we're trying to minimize surface area. You can see two variables here. So that means that I need another function to help me out. So if I get this volume function, and I know that my volume constraint is 500 cubic inches, then I know that 500 has to equal x squared y. And that means that I can use this equation to help me out, to help me get this surface area equation into just one variable. Okay? So I'm going to take this. You could solve for x or y. It doesn't matter. But this is going to be easier to solve for y because it just shows up one place over here. So y is equal to 500 over x squared. All right. And so I'm going to have surface area equals 2x squared plus 4x times 500 over x squared. Like this. And so you'll end up with a surface area equation, S of x equals 2x squared. We're going to have an x drop out here. 4 times 500 is 2,000, so plus 2,000 divided by x. Okay. And again, we could take this, derive it, find the critical points, etc. But again, I don't want to finish this out necessarily. I just want to show you how we would set this up and how we would approach it. Okay. So in this page, I've given you the objective functions and what I sometimes call the helper or the constraint equations. Okay. As it's just some examples to kind of, like I said, baby step into these. If you go to the back of the note page, in these ones, we're going to have a little bit less information. So I'm going to give you the problem. We're going to set them up, all right, but we're not going to finish them out solving. Okay, so before the first page, they were set up. Now we're going to set them up without finishing them out, and then finally in the next part, in the next video, we will actually solve these in their entirety. Okay, so let's look at number 5. Number 5, a farmer wants to create a rectangular field using a river as one of its boundaries. The farmer has 1,200 meters of fencing available and wants to maximize the area. So we have a constraint on how much fencing this farmer has. Okay, the river runs straight and will form one side of the rectangle, eliminating the need to fence that side. Okay, so let's look at what we have. 1,200 meters of fencing. Okay, that's definitely a constraint, and we want to maximize area. So what's our objective function? Well, our objective function is going to be the area function because we want to maximize the area. Before we jump into that, though, before we get ahead of ourselves, let's sketch the situation. So let's say that we have, the river right here. So this is the river, and this requires no fencing. Okay, and then we have fence over here, and then we have fence over here, and then we have fence over here. Okay, so this is fence over here, and this is as well. Okay, let's call this distance, because it's horizontal, let's just call this x, and then let's call this y, and if that one is y, this one also must be y, because this is a rectangle. Okay, what are our variables? Well, we have x is the width of the area, and y is the length of the area. Okay. What's our objective function? Well, as we said, we are trying to maximize the area of the field, so our objective function is going to be the following. It's going to be area equals, and for our diagram, it's x times y. Okay. What about the constraints? Well, we have a constraint on how much fence we have, right? We have 1,200 meters of fencing. Well, that means that this side here, and this side here has to add up to 1,200, okay, because that's the length of the fence. And so that's going to be 2y plus x equals 1,200, right? So there's a constraint, and you can see we need this because our objective function has two variables. So now we can use this to eliminate one of the variables. If we do this, if we solve this for either x or y, and I'm going to solve for x, I get x equals 1200 minus 2y. Then I can finally set up my optimization model, optimization function maybe. It's that objective function, but it's only going to have one variable in it. So it's going to look like this. Area is equal to x, and we just oops, I'm sorry, it's not going to be x, it's going to be y. And 1200 minus 2y, excuse me. Okay, so it's going to be, in place of x, we're going to put 1200 minus 2y, so 1200 minus 2y times y. Okay, and there's our optimization model or objective function in one variable. Okay. All right, so let's talk about package design here. Let's jump over to number 6. Excuse me. And again, we're not finishing out this to solve it. We would do what we did on the previous page, right, in the previous examples. Okay, so let's talk about package design here. Another common optimization problem. This company needs to design a rectangular cardboard box with an open top and a square base. Okay, that's going to be important. Open top and square base. This box must have a volume of 32,000 cubic centimeters. Okay, so that sounds like a constraint, right? We have to be exactly 3,200 cubic centimeters. The cost of the material is $2 per square centimeter for the bottom and $1 per square centimeter for the sides. 0 for the top because, well, there is no top. The company wants to minimize total material cost. Oh, okay, so there's what we want to minimize. Minimize total material cost. Okay, that is going to be our objective function then. It's going to be minimizing the material cost. All right. Let's give a little sketch of what's going on here. So let's see. So we're going to have a rectangular box, and it's going to have a square base. Let's see. Rectangle first. I'm not amazing at drawing three-dimensional figures here. Okay, so let's say that this bottom is a square, so maybe we call this x and x, and we call this y. Okay? All right, so there's our sketch. Clearly define our variables. We've got x is the dimension of the height, or sorry, dimension of the base. Y is the dimension of the height. I could have just written height, I guess, here. Okay. All right, now what's our objective function? Again, we are trying to minimize the total material cost, which means we want to minimize the amount of surface area. The amount of material is going to be the surface area of this object, okay? So what is our surface area? Well, it's the base, which is x squared, and then 4 faces, each face being x times y. Okay, so xy, 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 4 times. All right, so our surface area is equal to x squared plus 4xy. Now that's not quite the cost equation, but we can figure that out. So our cost equation, the thing that we're trying to minimize, the base costs us $2 per square centimeter. Okay, so $2 times the area of the base, whatever that is. Okay, plus the sides cost us $1. So 1 times the area of each side, so 4xy. There's our cost equation. That's our objective function because we're trying to minimize cost. What are the constraints? Well, we have this constraint on volume, right? 32,000 cubic centimeters must be the volume. So our volume is x squared times y, and it has to be 32,000 cubic centimeters. So 32,000 equals x squared y. All right, so what's our model then? Remember, this was our objective function. We have this expression here, and what we can do is solve this for x or y. I'm going to solve for y because, again, that makes substitution easier. So I get that y is equal to 32,000 divided by x squared. Then I can set up my model. It's going to look like this. Cost is equal to x squared, 2x squared plus 1 times 4 is just 4. So we're going to have 4x times 32,000 divided by x squared. Okay, if this is non-calculator, we're going to have to do some calculus to figure out the derivative and then the critical points. If we can use our calculator, we can just graph this and find the minimum, right? So I'm not going to take the time to do that. I want to jump on over to number 7. Okay, so let's look at number 7 here. Optimum path. So let's look at the situation. We have a hiker needs to travel from point A to point C with a river crossing at point B. Okay, so over here on the right we have the river is the distance from here to here is our river. Okay, all right. The hiker can travel on land at least 3 kilometers per hour and can use a boat to float down the river at 5 kilometers per hour. So he goes faster in the water because the river is flowing, so he goes faster in the water than he does walking through the woods, okay? The straight line distance from A to C is 10 kilometers, so you can see that in the diagram. The shortest distance to the river is 6 kilometers, so that is, if the hiker went straight to the river, that would be 6 kilometers, and you see that labeled in the diagram. The hiker wants to find the point on the river that minimizes the total travel time. We're going to ignore the width of the river because he has to cross the river, but we're going to ignore that as being negligible, okay? So this is our diagram of our situation. So then if the idea is if the hiker can float faster, then he can walk. There's some point in here where he is the optimum point to reduce time. If he goes straight to the river, that's the shortest distance to the river, but it's the longest distance overall, right? It's 6 plus this distance over here, right? That's the longest distance, so that's probably not optimum. If he goes straight from A to C, he's in the woods the whole time, and he's slower at walking. So there's probably a place, an optimum point, for him to meet the river that reduces the amount of time. In other words, the optimum amount of walking with floating in the river. All right? So here's how we're going to approach this. First of all, we need to know what this distance is here, from C to that point there. This is a right triangle. If you use Pythagorean theorem, you get that this distance is 8. All right. From there, we need to bring in some variables, okay? I am going to call this distance from this corner point here to be x. All right. If this is x, then this distance from C to B is going to be 8 minus x. 8 minus x. Total distance minus x. All right. Now, I want to define, so that's my variable here. I've defined that as x, so I'm just going to write x because I just explained what that is. I'm not going to write it out. All right, and then this distance here, but just to be totally clear, the path that the hiker is taking is walking right here. Okay, we'll do that in green. And then in red, floating down the river. Okay, so we need to know, well, how far is that, right, in green there? Okay, in green, that is going to be, if we use Pythagorean theorem, is going to be the square root of 6 squared plus x squared. That's 36 plus x squared. Okay. All right, so there's our distance from there. So if we wanted the total distance, it would be 36x plus x squared, square root of 36 plus x squared, and then it would be plus 8 minus x. That would be the total distance, but that's not what we're trying to minimize, right? Our objective function is going to be minimizing the total travel time, okay, the total travel time. So what's our objective function? Well, it looks like this. It's the time, the total time, right? So maybe we say that's like t total, okay? That's going to be equal to the time spent on the land plus the time spent on the river. So let's say, yeah, let's just call that t sub river, okay? So once we establish that, then we're going to figure out what that equation is for time, right? Because we know distance, but we don't know time. But we also have to remember that we do know that distance equals rate times time, okay? So time equals distance over rate, all right? So if I want the total time, for the time for land, let's call it T sub L, that's going to be equal to the distance on the land divided by the rate on the land. And the time on the river, T sub R, is going to be the distance on the river divided by the rate on the river. And we have both of those things, okay? So our optimization model is total time, so we'll just call that capital T, is going to be the distance on the land plus, distance on the land, which is square root of 36 plus x squared divided by the rate on the land, and we're told that is 3, plus the distance on the river, which is 8 minus x, divided by the rate on the river, which is 5. And then we would solve this by graphing. I would not give you this to solve algebraically or using critical points. And so this would be our model for time, all right? So that might be worth a rewatch, right? So all I did here is I took this time for land expression, plugged it in here, time for the river expression, plugged it in here, and that gave me my total time expression. And again, we would be looking for the minimum right there to minimize the travel time. That x would be that distance. Our answer would be that distance down the river where point B would be located.